Welcome back to another exciting chemistry lesson. In this video, we are going to learn about isotopes. Well, first of all, isotopes, they are different atoms of the same element. And on the periodic table, we see all those elements that have been discovered by scientists. But here's the key, not all atoms of the same elements are the same. And hence we have the term isotopes, because some atoms of the same element may have different number of neutrons. So basically isotopes are atoms of the same elements that have different number of neutrons. Now remember, we changed the number of neutrons does not change the identity of that element, but what we are going to change, we are going to change the mass, specifically the mass number of that isotopes, okay? So if we have more neutrons, the mass number of that isotopes increase, and vice versa. Then on the periodic table, every single element has an average atomic mass. Now the term average is referring to a combination, right, an addition, and then we divide by how many there are. So in this case, we are looking at the average mass of all the isotopes. And the average mass of an element is measured in AMU. And AMU is atomic mass unit. Okay, so here's the tricky part. When we look at this in terms of a sample, right? In this sample, there are different types of isotopes. So therefore, we're not only looking at the mass values, but there is another factor that determines the average atomic mass number, and that is the relative abundance. Relative abundance is, think of the term relative, it is relative to the total sample. And an abundance is basically how many there are in that sample. And this can be expressed in terms of percent or in terms of a decimal. Because when we have percent, we can convert that into decimal very easily, right? By dividing by what? 100. And now here's another trick. Sometimes they don't give us in terms of percentage or decimal, but they also give us in terms of a total atoms, and we have something to call fraction. Because once we get a fraction, we can convert to a decimal very easily, and then we convert to percent easily. Isn't that amazing? So don't get tricked by the basic math. And here is the tool that we use to determine the relative abundance and the mass of isotopes, and that is mass spectrometry. So we're looking at the mass of this right here. So this is an example of the data that generate from mass spectrometry. So here we have a mass spectrometry graph of boron, and in this case, you know right away we have the relative abundance in percentage, and this is out of 100%. Okay, so don't get tricked, okay? But in this case, if we look at this, we have the mass of boron in terms of B10. So this is your mass number. So it doesn't give you specific mass for that specific isotope for now, but in some case it will. So if we don't have that, then we have to use what's given to us as a mass number. So if we look at this right here, right, this mass spectrometry for the element boron has two isotopes. The first one is boron 10, and the second one is boron 11. And you can see that different isotopes have different relative abundance. And that's what determines the average atomic mass of the element. And you can see that we have a bunch of boron 11. So that means the mass is going to be near these values right here, okay? And we're going to show you that in a calculation later. So in this case, we have 20% of isotopes are boron 10, and then 80% of isotopes are boron 11. So of course, the mass number is going to be near this one, okay? So again, think of the term average. Now let's do a basic calculation. So when we put everything together into a formula, average atomic mass of an element is basically the relative abundance of that specific isotope times the mass of that isotope. So this is isotopes 1, okay, and this is isotope number 2, and so on, okay? And then we are going to add the relative abundance times the mass of the next isotope, and we continue to do until we have all the isotopes. So let's do a basic calculation right here. Here we have this element, and the mass spectrometry show that there are 3 isotopes, and this is the mass values that's given to us. Okay, these are mass right here. So the mass of each isotopes, okay? And then here, instead of giving us in terms of percentage or decimal, it gave us in terms of the number of atoms. But that is okay. We can look at this graph the y-axis, and we know that's from here to 5, so each one of them must be 1, 2, 3, 4, 5. So right here, how many atoms of this isotope do we have? So going across, we have 2. That's easy. Then right here, what do we have? 3. And right here we have 5. So we have 2 plus 3 plus 5. What's that going to give us? A total of 10. So now we can generate a relative fraction. So in this case, we can divide by the total 10. Divide by the total 10. It doesn't have to be 10, okay? So don't get tricked by this. We just make it 10 because it's easy for us to calculate. So in this case, we are going to convert those fractions into decimal. So that's pretty easy. 0.2. This is 3 divided by 10 is 0.3, and 5 divided by 10 is 0.5. And now we have the relative abundance in decimal, which then we can multiply it to get our average atomic mass. So let's go back over here. We have what? We have this equation. Again, go back to the idea. We have this equation, relative abundance times the mass. So we have 0.2 times 291.1. Okay, that's isotope 1. Then we go on to isotope 2. So we have 0.3 times 292.1. That's the second isotope. And we continue. We have 0.5 times 293.1. And notice how the relative abundance of this one is 0.3, which is 30%. This is 0.5, which is 50%. So you expect that the average atomic mass is somewhere between these two values right here, okay? Because look at this. This is what we have most abundance of. So let's look at the math. I plug in the calculator. So we're going to calculate everything on a calculator. We have this 292.4 AMU. So right there, that is our average atomic mass for this particular element, okay? So 292.4 AMU. As you can see, this is between this isotope and this isotope, okay? And that's how we can look at the graph to kind of make a good estimate. What is the nearest average atomic mass going to be? Now let's look at this one. We have seen this already, right? But in this case, notice how I changed so that's no longer B10, but we can see that we have specific mass for boron 10 and boron 11. And in this case, what we have? We have percentage. So that's pretty easy. So here is 50%, so right here must be 20%, right? Because 1, 2, 3, 4, 5. And here we have 6, 7, 8, so this must be 80%, okay? So now let's do the basic math we have. Again, convert your percent to decimal. We have 0.2 times 10.1 plus 0.8 times 11.1. Then the next step is we are going to plug in our calculator and we're going to solve it, and this turned out to be 10.9 AMU. And as you can see, right, look at this, we have relative abundance of 80%, so of course the mass must be near to that. See how relative abundance works? So it tells you, so that way you can make an estimate. Where's the mass, where's the average atomic mass going to be? So in this case, we have 10.9, okay? Now let's go back and plug in and check our answer. And as always, if you need more practice, go do some more practice problem, okay? So now let's go check our answers. So click submit and finish. Now let's go check the second one, submit and finish. And there you go. Let's see what we get on our answer. And that's all we have to do. So again, that is how you use mass spectrometry to understand the concept of isotopes and how we calculate our average atomic mass based on relative abundance and the mass of different isotopes for that specific element. And as always, if you have any question, take a picture of your work and put it in the forum and we will help you from there. And we'll see you next time on another video.